Okay, so welcome to the next part of the lecture, and in this part of the lecture, we're going to be looking at growths and decays. So in the previous lecture, we talked about linear relationships, so how we could fit a set of data to have this straight line. And perhaps we could say if we have this positive correlation or this negative correlation, something that looks a little bit like this, we maybe have two variables, maybe A and B. But what we can say is we have some sort of proportional, can't even write, well, some sort of proportionality. So we say that A is proportional to B. Or perhaps we could say, in this case, A is proportional to 1 over B. We have some negative proportionality. So, okay, so this is what if we have a straight line, but what happens if we have something that looks a little bit like this? What happens if our data decays? So, for example, this is radioactivity. This is quite important. If our data starts, if our maybe our mass of our if our isotope starts big, over time it begins to decay quite quickly, and it actually loses half of its mass per each time step. Likewise, if we have something where we might have a bacteria, we might see it grow exponentially like this. We might see it grow um, as an exponential growth. So we can actually begin to describe what these would look like. So generically, we could say that our y is equal to AB to the x, which for this kind of plot, our decay, we would say that, well, this would be our b value would be some sort of constant. So this would be y equals a1 minus r to the x. And likewise, if we have a positive growth, we would say that this equals y equals xa1 plus r to the power of x. So this would be our exponential decay and our exponential growth. Okay. So what happens if we actually want to physically describe something? So let's again take an example of radiation. So um, if we think about maybe an isotope, what we say in the book, iodine-125, well, we know that it actually has a half-life. So a half-life means that at this point in time, it's lost half of its mass. So if we take iodine-125, we can see that its half-life is around 61 days. So that means after 61 days that it's lost half of its mass. So if we started with a mass of 1 kilogram, after 61 days, this would be zero point 0.5 kilograms. So this would look a little bit like this, and this is how an exponential decay grows, or is shown. So how can we describe this? Well, if we go back to our logs a few weeks ago, we can actually begin to think how we might rearrange this information to kind of describe what we want to show. So maybe we call our n here, our mass or our number of atoms, n, and we're going to call this time at the bottom, and this is going to be in days. So we can create this relationship. We know from our laws of logs that we can actually tidy this up to actually create this relationship, to create the relationship of a linear straight line. So what we would say here is that our initial mass, n, is, well, our current mass area is equal to our initial mass multiplied by e to the minus kt, where k is just a constant, which is our time constant. E is the natural E, which we should look before, which is just, again, it's a mathematical constant, which if you want to spend some time looking at, you can go and derive. And we then have our two values here. So let's put some real numbers onto this. So potentially, if we have something like the example we've got given here, where we can say that we have originally 125 atoms, so it's iodine 125. So what we can say is, well, our initial information here would be 125. Our half-life, well, if after we know after half the time it's lost half its mass, so that would be 125 divided by 2, and that is equal to minus 61, the time in which it's happened, multiplied by our constant k. And what we can do is, well, we can use our rearrangement, we can use our laws of logs, that should be an E here, and that can help us find out what this k is, right? So let's just rearrange that and get that into our straight line, what we would hope. So we know if we multiply through by ln, we'll get our natural log. So that would be ln 125 divided by 2, and that is equal to ln 125 minus 61k. It's just the law of logs. Remember that if we have something to the e, we can multiply. When we have an e value here, we can multiply through and we can bring this value down. Go back to the end of the lecture on logs if you've forgotten about these rules. So what does this mean? Well, actually, we've created quite a nice relationship. And let's put these numbers back from here. So we've now, if we have this n, what we have previously, we can say that is ln n is equal to minus 61k plus ln n0. Okay, what does that look similar to? Well, actually, we can see that that is in the form of y equals mx plus c. So if we were to plot this, what it would actually look like with our ln's, so ln n, and our time on the bottom, is we now see that we can condense this curve that we have here into a straight line, and we can describe that with y equals mx plus c, or ln n equals minus 61k plus ln n0. Oh, that's our intercept here. So it's just following exactly the same rules, and we can actually begin to solve our k, and all our k is our gradient here. So to solve our k, all we need to do is we can say that ln n over ln n0 equals minus kt. So we put our numbers in and we will find out that that would be 4.135 over 4.828 multiplied by minus 1 over 61 equals k. So that means our k value, they're always quite small, would equal minus 0.0140. So we now have a full description of this curve. So this is really important if we have some sort of bacteria which is growing. We can actually begin to fit this model to it, which can actually help us describe using straight lines, using an equation, what is happening with the data. We'll go through a quick example, and then I'll actually show you how we can apply these logs, and we can actually begin to solve fitting data points using the log. So here we go. Our first example is a strain of bacteria growing on your desktop doubles every 5 minutes. Assuming that you only start with one bacterium, how many bacteriums could be present at the end of 96 minutes? So again, so we're actually looking at the opposite direction here. So this is our line's going to go in this direction. We're looking at how things grow. I've used the example of bacteria. This is typically how bacteria multiply. And what we'll start is we'll actually begin by maybe take this equation here. So I've written it as A in the book. So we'll say that A equals A0 K X. So, right, we can just begin to fill some numbers in. So if we say that our original value, our original number equals 1, we want to try and find out what can happen as we get to at the end. So so our strain of bacteria doubles every 5 minutes. So we know our original value for A is 1. It doubles every 5 minutes, which would mean 2. And then that means that if we have E, we have K to the X. So our initial thing to do here is we're looking to find this K value. And what this K value means is we can begin to model. So a little bit like when we have our straight line plot, maybe we only have something which is this long. Well, once we understand this information of our gradient, we can extend this and extrapolate this into the future. And this is basically the foundation of all models. So now we have this, we can say that 2 equals 1 e k to the 5. And then we can say, well, let's actually solve for k. So that would be ln2 equals ln e to the 5k, which then disappears. So ln2 would equal 5k. And then we can say that k equals ln2 divided by 5. And we find that k equals 0.1386. Okay, so we have our constant, which is great. So we've been shown originally that a strain of bacteria doubles every 5 minutes. So we've put this into our equation, which is then going to help us project forward into the future. So all we need to do now is say, well, we want to find out our number A. We know that our original value was 1. We'll write our equation back here just to remind us. So A equals A0 E k to the x. So we can say our original value was 1. Then all we need to do is then multiply this by our value here, which is 0.1386, and multiply that by our 96 minutes. And we can find that our A would be 602,249 bacteria. So that means that after 96 minutes, we now have this many bacteria, but after 5 minutes, we only had 2. So this shows how this exponential decay increases. So with what we've shown here is after, if this is our original point where 1 minute we have 1 maybe, so 1, we could show at 2 minutes, at 5 minutes, sorry, we've doubled our data. So we have something like this. And then we'd have to extrapolate the data graph all the way up to here. And we'd say after 96 minutes, we've had this decay that looks something crazy like this. So our number of bacteria are quickly and rapidly growing. So that's just how our growths and decays work. It works in both ways. You're just following the formula, but remember, don't be tripped up by the laws of the logs.